All right, welcome back everyone. We are continuing our discussion about the simplex method. So let me remind you where we are and what we've said so far. How far have we developed it? So we're talking about linear programs in standard form, sometimes called canonical form. Minimize C transpose X subject to AX equals B. A is an M by N matrix, and in all examples of interest, M is strictly less than N. It's certainly less than or equal to N by definition, because we've assumed that the rows that the rows of A are independent. So if M is equal to N, then the problem is has one unique point, so not very interesting, and X non-negative. And we have discussed so far that in our discussion about the geometry of linear programming, that the extreme points, the corner points, if you want to think about it, of the feasible set, are really combinatorial in the sense that they are exactly, they're unique, they're defined by choosing M of the columns of A. Or another way to think of it is that we need N minus M of the entries of X to be set to 0, and then the remaining M elements are determined by A. So our notation, but by the M equations. So our notation from last time is that B is called a basis, and it is an index set that is a subset of, this is my notation for the elements 1, 2, 3 up to N. The magnitude, the cardinality of B is equal to M, and as soon as you choose B, the solution is immediately has to be of the form xb. Remember, again, I'm abusing notation and rearranging the coordinates in order to represent it in this more convenient way. 0, where xb is chosen, and the only way that will satisfy the M equality constraints AX equals B. Therefore, xb is AB inverse times B, and the remaining elements are equal to 0 for any I not equal, not an element in B. And as we saw in the discussion, it may be that some elements of XB are also set to 0, but that they're not forced to be 0 by our accounting of making sure that we have N equality constraints. They're set to 0 just because of this this equation. So this is how extreme points are defined. And what we discussed in the previous lecture is that we move from corner point to adjacent corner point by changing the basis. So we move to an adjacent extreme point, or let me use the notation that's used for in the context of the simplex method, basic feasible solution. We defined that last time, by choosing a new basis, B new, that has one element difference from the old B. So in other words, the cardinality of the intersection is M minus 1. That just means that I've introduced one new element in the basis, and that means I need to get rid of an element. So B new is equal to B minus some J hat and union some I hat. So I hat enters, J hat exits. And we discussed in the previous lecture how how we do this procedure of I hat entering and J hat leaving. So we found that if let me make sure I have my notation from last time correct. Yes, I was using I hat. So what do we? How did we write it last time? X new is equal to X old plus theta times the direction D. And what do we know about D? Well, D has to have a 1 in the I hat location. It has to be 0 in all locations that are not I hat and not in the old B. And we don't know what, for now, what dB is. And we computed, so this is again the I hat location. And dB is just determined by the requirement that A of x new has to equal B. And since x was feasible, this means that AD is equal to 0, which means that dB is equal to minus AB inverse times AI hat. So this is how D changes. And then we also talked about how we determine theta. So theta is given by, so you can see what's going to happen, x plus theta d. As theta increases, we discussed that theta has to be non-negative. Could be 0. Has to be non-negative, though. And as theta increases, we're going to stop when one of the basic variables becomes 0. And that is the variable that exits the basis. That's our j hat in the notation of this slide. And so this is how we determine theta. Now, if dB is all non-negative, that means that theta can increase forever. And that means we found that means that our polyhedron is unbounded, and in particular we found a direction in which it's unbounded. So so theta is equal to the min over all j such that dj is positive, and xj divided by dj. And again, we get this immediately by looking at this equation, looking at this expression for x nu, and the requirement that x nu has to be non-negative. Okay, so this is where we are. What we haven't discussed so far is the objective function. So how does that change our value? And also, how is this going to help us choose a good neighboring corner to move in? Because there's going to be some corners that make our lives worse. And this brings in the very important concept of reduced cost. So the main question we want to know is, okay, we moved to a neighboring element, did we improve? Did we improve? Is x new better than x old? And that, of course, just means, is x new less than C transpose wherever we previously were? And we've got all the expressions we need. We just basically plug this in. So we've said that x new from the previous slide is equal to x old, which is xb in 0, minus theta times AB inverse AI hat 0 plus theta times EI hat. Okay, so all I've done here, let me flip to the previous slide. I just wrote out this expression component-wise, or actually I just separated out that one. And so therefore, C transpose times x new is equal to CB transpose XB plus CB complement transpose zeros minus theta times CB transpose AB inverse AI hat plus theta times C transpose EI hat, which is just CI hat. And if I now ask, what is the difference? Let's look at the difference between CX new minus CX old, my improvement. CX new minus CX old. Well, I never called it old, so let me not do that. Let me not start now. Just call it x as x old. This is, of course, this value here is cx old. So I'm just subtracting that, moving that to the left side. So this is equal to theta times the per unit increase. You can think a decrease. And that is going to be ci hat minus cb transpose ab inverse times ai hat. So what is this? This tells me how the rate of decrease, how much I improve if I go in the I hat direction. So this is so important here that we call this the reduced cost of I hat. So it says if you put I hat into the basis, if I hat was not in the basis and you put that into the basis, what exits the basis, as we said, is completely determined by our calculations on the previous page. And how does the cost change? The cost changes by the reduced cost of I hat times however much you're going to move. But like all convex optimization, we're going to make local decisions. So one way to choose, we're focusing on how much do we infinitesimally improve. So for now, we're not going to worry about theta. Although we could presumably make our decisions based on estimates or even calculations of how big theta is. But for now, let's not worry about that. We're defining this concept of reduced cost. So when is I hat a promising element to introduce in the basis? It's promising if the reduced cost is negative. So let me make just the definition a little more carefully. Let me call, and I'm going to use more or less standard notation that you'll see. So the reduced cost of any element I is how much you would benefit infinitesimally by introducing I into the basis. So Ci bar is the notation we're going to use for the reduced cost. And this is defined as Ci minus just what I've written above, but now for a general I, not necessarily the I hat that we happen to introduce into the basis. Ci minus Cb transpose AB inverse times AI. So a few, so let me put this in a box because it's so important. So this is a reduced cost. And a few immediate observations here. If I is already an element of the basis, then we would expect this to be 0. That's our intuition, but we don't have to rely on that. We can just look at this equation, and you'll indeed see that AB inverse times AI, if I is an element of B, is just going to be the ith standard basis vector, which means that it's going to just pick out Ci. So the reduced cost is 0. So if I is in B hat, then check for yourselves, do the calculation to make sure that you agree that the algebra bears this out. Ci bar is equal to 0. What else is immediate? If for some I, if Ci bar is less than 0, then we might improve by adding element I to the basis. Why did I say we might and not we do improve? Because theta could be 0. So only if theta is strictly positive do we actually strictly improve when Ci is negative. But by the same token, if we are sitting at an extreme point, we compute our reduced costs, and we find that all the Ci's, so I'll just summarize by the vector C bar, if all the reduced costs are non-negative, this is now a certificate. It's a guarantee that we're sitting at the optimal solution. this is really important. So important that I will put a highlighter through it. It is a hallmark of convex optimization that we're able to come up with succinct certificates of optimality. Though this is now specialized to a very limited class or very special class of optimization problems, namely linear objective, linear constraints, and to a very special form of even linear optimization, namely linear optimization in standard form or canonical form, this is really an expression of the KKT conditions. So we'll be getting into this a little bit more, but I encourage you, if you've seen the KKT conditions, to try to unwrap all of it and see how it is that this special set of calculations basically is an expression of the KKT conditions. So now this brings us to the end of our conceptual simplex method. Conceptual because I said that the simplex method tells us that we move from corner to corner, and we've now talked about how the mechanics of actually moving from corner to corner, what that means, namely choosing a basis that overlaps in all but one element. And also we've talked about reduced costs. Reduced costs, which are calculated at every extreme point, the reduced costs are different. The reduced costs tell us what are what is our possible benefit of introducing any given element I that's not in the basis into the basis, and this also tells us a stopping condition. So again, very briefly, our summary is as follows: at a point x equals xb and 0, we know that xb is equal to a b inverse b, and we know that reduced costs are equal to c minus cb transpose a b inverse times a. And if c bar is greater than or equal to 0, then x is optimal. And otherwise, we pick some I hat such that c I hat is less than 0. We compute db, which is equal to minus ab inverse ai hat. We compute theta, which is equal to the min over all j such that dj is positive, xj over dj, and this gives us the new b, the new basis b, and therefore x new is equal to x plus theta d. Again, di hat is equal to 1 here, which is equal to xb new 0, where xb new is b new inverse times b. Oops, sorry. xb new is equal to a b new inverse times b. This is conceptual because we've just describing the basics and not giving the specific algorithmic mechanics of the simplex method. Now, just wrapping up, I want to say a few things about computational considerations. So first, a very naive implementation could have us cycle forever. We could potentially cycle forever if the problem is what is called degenerate. This was introduced at the end of the last lecture. It's when a particular extreme point has many, or has more than potentially more than n equality constraints that define it. So again, think about a diamond where it has many bevels. That corner point on top, this is what I tried to draw on the last slot on the last lecture, has many equality constraints that are tight there. And in that case, you could be switching basis and not moving. But a simple fix, for example, if we just agree that we will break ties always in, say, lexicographic order, or you specify a particular order, and you always break ties in this particular way, this can fix this cycling forever. And if you do that, so let's say simple fix guarantees that simplex terminates in finite time. With the exact solution, again up to the precision of our arithmetic. On the other hand, this could take exponential time. Exponential, again, in the description of the problem. As we said, the cube has just 2 n constraints, but 2 to the n corner points, and it is possible to arrange it just so, to choose an objective function and choose the corners of the cube, position them in such a way that a simplex algorithm with a particular tie-breaking rule will visit exponentially many corners, always improving until it gets to the optimal solution. We've only recently learned through a kind of analysis called smoothed analysis, we've understood why in practice this behavior is not observed. But this is not the topic of this class. I'll just give the hook here. A smoothed analysis basically tells us that this doesn't happen. So we're going to leave that aside. Now, back to the algorithmic step aspect of each iteration, what is the computational bottleneck? It's really this calculation of A, B inverse. And this can be done in a more efficient way. We're next going to talk about more specifically how simplex method is run, and we're going to talk about the algorithm in the context of what's called the simplex tableau. So we're going to pick this up. Next, and it's going to help us in our discussions of duality subsequently, and then many other things we're going to do in this class.